So we have talked about the center and shape of a quantitative variable, and the last thing that you would want to know about a quantitative variable is the spread. Just like with center, there's multiple ways that you could measure spread. The most common one is probably the standard deviation, which is where you take each individual data value x, you subtract off x bar, that's the mean, you square that thing, and then you sum it all up. So this is the summation notation. You divide that by n minus 1, and then you take the square root of the whole thing. If you are doing this about a sample, we call it S, and that's when you would use X bar. If you wanted the population parameter, you somehow had the standard deviation of the whole population, it would be sigma, and you'd need to use mu instead of X bar. So standard deviation tells you how much the data deviates from the mean on average. So you can sort of see, we're taking each data point, we're subtracting the mean, we're dividing by something kind of like n, so it's basically like the average deviation. And that's why I'm showing you the formula. I wouldn't expect you to compute this by hand, but I think it helps you understand that that's what standard deviation means. If you have a larger standard deviation, your distribution has more spread. If you have a smaller standard deviation, your data has less spread. So let's look at two different distributions. If we were going to try and characterize the center of this first distribution, I would say that it's centered at 0. If I had to characterize the second one, I would also say that its center is at 0, because I can see that's sort of where the middle is, the most common. If I had to describe the shape, I would probably say symmetric and bell-shaped. And the same thing for the one on the bottom. The shape is symmetric and bell-shaped. But clearly there's something different about these distributions. This one looks much skinnier, whereas this one looks more spread out. So the thing that's different about these distributions is the standard deviation. The standard deviation in this one is 1, and the standard deviation in this one is 4. So there's a much larger standard deviation in the bottom one. We've got a rule called the 95% rule, which is that if a distribution is roughly bell-shaped, about 95% of the data will be within 2 standard deviations of the mean. So if we think of this as x bar, and then maybe we go out x bar plus s, and x bar plus 2s, and here this is x bar minus s, this is x bar minus 2s, we're going to be able to estimate that about 95% of the data is in the middle of the distribution. That means I've got 5% left to add up to 100, and I get 2.5% in each of the tails. So this is useful for a number of reasons, but one of the reasons is if you know that 95% of the data is within 2 standard deviations of the mean, then you can use that to estimate the standard deviation from a plot. So I'll show you what I mean. This data is the number of hours worked last week from my general social survey. And I think we can see, it looks like it's centered around 40. There's a big spike here, and it looks roughly symmetric, and it's not quite bell-shaped, but let's say that it's good enough. So now we're gonna guess, where do we think 95% of the data is? Probably between like here and maybe here, something like that. So I know that my mean is 40, and this looks like it's going down to like 10, and this looks like it's going up to 70, so that's about 30 in here and 30 in here. So if 30 is equal to 2 standard deviations, divide by 2, 15 is approximately the standard deviation. And I think it was actually like 14 or something. I looked for it. So it works pretty well. It's a nice, quick way to estimate the standard deviation. And you can also use it to answer questions like this. So the penguins data set, which I think you looked at for one of the labs, had a bunch of different species of penguins. One of the species is Adelie penguins, and the distribution of bill lengths for those penguins is roughly bell-shaped. The mean, or the x-bar, was 38.8, and the standard deviation is 2.66. And then the question is, if I wanted to say 95% of bill lengths are between this and this, how would I create an interval to do that? And maybe we'll talk about that when we have synchronous class together. There's also an idea of z-scores. So a z-score is a way to standardize your data by subtracting off the mean and dividing by the standard deviation. If you had a population, again, you'd use mu and sigma instead of x bar and s. And the process of making a z-score translates the values from your original data space into the number of standard deviations from the mean. So the mean has a z-score of 0 because the mean minus the mean is 0. Anything, 0 divided by anything is 0. And you can interpret that as the mean is 0 standard deviations from the mean. Makes sense. And all other values you could say, oh, this is 1 standard deviation. This is 1.3 standard deviations from the mean. And because of the 95% rule, if the distribution is bell-shaped, then 95% of z-scores are between -2 and 2. So let's practice making some z-scores, remembering that a z-score is x minus x bar over s. So Adelie penguins' bill lengths have a mean of 38.8 and a standard deviation of 2.66. And then we've got their flipper length, and that has a mean and a standard deviation as well. So let's think about a penguin on Torgerson Island with a bill length of 44.1 millimeters. So if I wanted to find the z-score for that, I would put in that penguin's bill length, 44.1. I would subtract off the mean, 38.8. And I would divide by the standard deviation, 2.66. And I'd get 5.3 divided by 2.66, or 1.99. So it's almost 2 standard deviations above the mean. That means that penguin has a pretty long bill length. And then I could see about its flipper length. Is its flipper length also extreme? Is it just a really big penguin? So let's find the z-score for its flipper length. Again, I'm going to put in its actual flipper length, 210, and then I'm going to subtract off the mean, which was this 190. And then I'm going to divide by the standard deviation of 6.54. So I get 20 out of 6.54, and that's 3.06. So it's more than 3 standard deviations above the mean for flipper length. So if I had to think about this first penguin, the flipper length is more extreme. It has really long flippers, 3 standard deviations above the mean, outside the range where we'd expect 95% of penguin flippers to be. And I think I'll leave the other problem for you to work on, and then we can talk about it in synchronous class. We've got some other ways to characterize distributions to talk about spread. So we might be interested in the range of a data set. The range is the maximum minus the minimum. You could also sometimes just compute maximum and minimum values. Sometimes we want to know the quartiles. They're kind of like medians. They're the median below the median and the median above the median. And sometimes we take our maximum, minimum, Q1, Q3, median, we put them all together into this 5-number summary, where we go the minimum, Q1, the median, because Q1 is right in between these two things, and then the median, Q3, and the max, because this is right in between there. And this breaks the data into chunks of 25%, 25%, 25%, and 25%. So it's a nice way to break up the data. Sometimes people will also compute the interquartile range, which is just Q3 minus Q1, sort of like a range, but instead of going maximum minus minimum, it's just for those quartiles. And let's think about the idea of resistance. So when we talked about measures of center, we said that the mean was not resistant and the median was resistant to outliers. So what do you think about the measures of spread? Which of these are going to be resistant and which won't be? And I'll ask you about that when we get to synchronous class. And then the last thing that I'd like us to think about, again, is just estimating values from plots. So we might want to estimate the x bar, the standard deviation. We might want to do the 5-number summary. So that's the minimum, the Q1, the median, the Q3, and the maximum. And the measures of center for things that are bell-shaped like this are basically the same. So the mean and the median will be similar to one another if you have a bell-shaped distribution. So I would probably say that my estimate for the mean is 190 and my estimate for the median is also 190. And I'd like you to try to estimate the standard deviation, the minimum and maximum, and see if you can come up with a guess for the Q1 and Q3. I think those are the hardest ones, and we can talk about that in synchronous class.